Hello geometry students, in this video we are going to prove this theorem. It's the inequality of opposite angles, and I put this in parentheses because I don't really know the official name of the theorem. This is Theorem 5.10 for the students who are in Mr. Wen's classroom. So I guess it's better if I just state this theorem and then prove it afterwards, so it'll be a little bit more clear. So the theorem says, if one side of a triangle is longer than another, then the angle opposite the longer side is greater than the angle opposite the shorter side. Now that's a whole lot of words here, so let's see if we can illustrate what this means. So if one side of a triangle is longer than the other, so let's make this if statement here. If BC, and we'll let BC be the longer side, is longer than another, so let's say that BC is longer than BA. Okay, so if BC is longer than BA, then the angle opposite the longer side, so the angle that's opposite from BC is angle A. So I'm going to say then the measure of angle A, then the angle opposite the longer side, so that's angle A, is greater than the angle opposite the shorter side. So BA is the shorter side. The angle that's opposite of that is angle C. So measure of angle A is greater than the measure of angle C. Okay, so I have a longer side and a shorter side, and the angle opposite from the longer side is bigger than the angle opposite the shorter side. Okay, so that's effectively what the theorem is saying. There's a ordering of sizes between angles and sides in a triangle, and they correspond. The longest angle is across from the biggest angle is across from the longest side. The smallest angle is across from the smallest side. And so let's try and prove this theorem. And this theorem is a little bit different from anything else because we're proving an inequality. We're used to writing congruence proofs, but now is the first time that we prove an inequality. Okay? So we're going to make use of a great little postulate that's known as the Ruler Postulate. So the first thing that I am going to do is find the length put my ruler on here and make a mark for the length of AB, and then duplicate it on AC. So I've made this mark here. And the Ruler Postulate is so nice because it says that if I have a length, I can replicate it anywhere. So I'm going to replicate it along BC. Okay. So in my first statement of the proof here, I'm going to say construct point D, clean this up here, point D on BC so construct point D here so that BD equals BA. Okay, so construct so that these two segments here are equal, and I can do this using the Ruler Postulate. If I have an existing segment, I can replicate that length anywhere else that I want. Okay, and this is going to be very helpful to my proof, and you'll see this in just a minute. So next thing I'm going to do is connect A and D. So we're going to connect A and D. And that's really kind of the Ruler Postulate again. It says that if you have 2 points, I can connect them with a straight line. Okay? All right. Now, with this in mind, I am going to start naming some angles in here so that it's going to help me a little bit more in my proof. So the first angle that I'm going to name, this is angle 1. Right here. That's angle 1. This down here is angle 2. Okay, let me write my 2 here a little bit better. Angle 2. And then this over here is angle 3. I'm sorry, actually I want this to be, I want this right here to be 2, and I want this down here to be 3. Okay, so let me draw my picture back in there. Okay, so I have angle 1, angle 2 and angle 3. Now, what I can say here is that angle 1 and angle 2 have to be congruent to each other. And this is using the base angles theorem. So the measure of angle 1 is equal to the measure of angle 2. And this is using base angles theorem. And so you can look back in the videos in chapter 4 to view a proof on the base angles theorems. But because this is an isosceles triangle, these two angles down here have to be congruent to each other. Now, let's look at the left side of this here. I have angle 1 and angle 3. So what this tells me is that the measure of angle BAC is equal to the measure of angle 1 plus the measure of angle 3. Okay? And this is the angle addition postulate. 1 and 3, when you add them together, they make BAC. Okay, so let's write this in here. Giving my reason here, this is angle addition postulate. Okay. And the reason I'm writing this statement here is that it's going to allow me in my next step to write a statement of inequality. Let me just separate these two here. So what I can say next then is that BAC has to be bigger than the measure of angle 1. Okay? Because BAC contains 1 in it, 1 plus 3 equals BAC, therefore BAC has to be bigger than 1. So the measure of angle BAC is greater than the measure of angle 1. And I'm omitting some of my reasoning here just because I'm running out of space, but it's because BAC contains the measure of angle 1. Okay, so I'm going to set this statement aside for a minute. Well, actually, I'm going to take this one step further, and I'm going to say that the measure of angle BAC is also greater than the measure of angle 2. So that's going to be very important to me. Okay, so this is greater than the measure of angle 2, and my reasoning here is substitution. Two and 1 are congruent, so I can take 2 and I can substitute in here for 1 and say that BAC is greater than the measure of angle 2. Now, and I'm just trying to give you a big picture of where I'm heading with this. What I'd like to say next is that the measure of angle 2 is bigger than the measure of angle C. So I have now measure of angle A is bigger than measure of angle 2. I want to say next that 2 is bigger than C, because if 2 is bigger than C and A is bigger than 2, then A has to be bigger than C. Okay. So let's look at angles 2, 3, and C. And this involves a little bit of remembering something from the previous chapter. But if you can see here that if you look at this smaller triangle down right here that I'm kind of shading here in green, 3 and C are interior angles and 2 is an exterior angle. So there is the exterior angle theorem, which says that the measure of the exterior angle is equal to the sum of the measure of the interior angles. So I can say the measure of angle 2 is equal to the measure of angle 3 plus the measure of angle C. And this is the exterior angles theorem. Okay. And we're going to follow similar logic to what we did over here. Because C is included as part of angle 2, I can say then the measure of angle 2 is greater than the measure of angle C. Okay? C plus 3 is equal to 2, therefore 2 has to be bigger than the measure of angle C, because angle 3 is definitely not negative, so 2 has to be bigger than C. Okay. And now look what I have here. These are two very, very useful statements that I can put together now. BAC is bigger than measure of angle 2, and measure of angle 2 is bigger than the measure of angle C. So now I can write it this way. Measure of angle BAC is bigger than the measure of angle 2, which is bigger than the measure of angle C. which means that the measure of angle BAC has to be bigger than the measure of angle C. Okay. But notice here that BAC is the same thing as angle A in the picture here. We just drew some other stuff in there, but angle BAC is the same thing as angle A. So then I can just write in my last statement here, the measure of angle A is greater than the measure of angle C. Let me move this up so you can see it correctly. And there it is. That's the end of my proof. The key step here is making this mark right here, this point D, so that I have an isosceles triangle inside of the other triangle that I'm using. But once I do that and follow all the steps, you can see that the measure of angle A has to be bigger than the measure of angle C. And this theorem, Theorem 510, there's no official name for it, but it's fairly important because it is used as a key part in the triangle inequality theorem, and that's one of the later videos.